In this tutorial, we will review the AdamW Optimizer, which is currently the state-of-the-art in most deep learning training regiment. We're also going to code it with NumPy, and you'll see it's like 10 lines of code. AdamW is a variant of Adam which apply regularization in the form of weight decay in a very specific way that makes it much more stable than the regular Adam Optimizer. We'll break down where this regularization helps and how it differs from the traditional Adam plus L2 regularization. For those that don't know me, I'm Yassine, a published researcher and machine learning practitioner who loves to teach. Do consider subscribing to the channel to learn technical topics related to machine learning. Throughout this tutorial, you will see me draw around a free digital whiteboard called L2, who are kindly sponsoring this video. If you watched the live stream where I explained deep learning paper or my tutorial for the past year, you saw me using that whiteboard a lot. The workflow I like the best with this whiteboard is I take a screenshot of everything that is relevant and then I put it into like one big collage and I draw arrows in order to kind of link the stuff together or scribble around to explain my thought. Two features I really like with L2 is first like the freehand drawing tool is very intuitive and it's super simple how to use it, right? And I literally just I just write with the mouse and it still works super fine. Second thing I really like, right, is these arrows. I don't know why I love them so much, but like you can be very precise about like what you want to show, and then you can kind of edit them to kind of have like a good tracking, and like it just stays at the right spot. So if I hit 6 here and I want to show that this is Adam with the regularization, I get that. They also have an SDK if you are a developer and want to add a whiteboarding functionality to your app. It's all React based. So as you can see over here, this is the L2 SDK that is being used, and then there's an agent that is kind of working at the same time as the person that is drawing, right? So you can shoot it some task on the right hand side, and then you can still manipulate the whiteboard while the agent is kind of working and also manipulate the whiteboard at the same time. Pretty cool. So you can go to L2.com, which is literally the whiteboard, so you can start to play with it. You can also go to L2.dev to play around with the SDK. So check out the link into the description, and big thanks to them for making this technical tutorial possible. So let's review quickly where AdamW will fit in a deep learning setting and what element of the neural network its regularization is affecting. Let's start with a basic neural network. Data comes into the input layer. It gets linearly transformed by the bias and weights of each neuron. A nonlinearity is introduced after that, usually a ReLU. That process is repeated at each layer until the output layer, which output a class or a number for the data point. Now that we have a label, we can calculate loss, which is task dependent. All previous gradients are set to 0 before a new gradient with respect to that loss get calculated starting from the end of the network until the first hidden layer. When all gradients are calculated, the Adam Optimizer comes in and will update the weights in a specific way using the gradient information. The vanilla version of Adam, you can get some pretty good results, but you usually apply some form of regularization on this process to obtain better generalization that doesn't fit the noise in the training data. At this point, there are multiple types of regularization you can use to make this generalization more likely. Let's go through a few of the main ones. First, we have L1 and L2 regularization, which both affect the loss and subsequently the gradient calculation. L1 adds a penalty term to the loss function that is proportional to the absolute value of the weights. This encourages sparsity in the model by driving some of the weight down to 0, which is useful for feature selection. L2 adds a penalty term to the loss function proportional to the squared magnitude of the weight. This prevents weights from growing too large, which promotes smaller and smoother weights. The second method is data augmentation. Data augmentation is pretty simple. It modifies the training data by applying random transformation like rotation, cropping, noise, flipping, all sorts of stuff to generate additional diverse training example. This improves generalization by exposing the model to more variation of the data, but doesn't touch the weight or loss directly. Then we have the dropout method, which randomly set to 0 a subset of activation in the neurons during training with a certain probability, usually something like 0.5. This prevents co-adaptation of the neuron and forces the network to learn redundant representation. This also does not affect the weight directly, but influences the gradient indirectly. Then we get into the weight decay method used in AdamW. This method adds a term to the weight update rule, decaying weight directly during optimization. This has a similar effect on L2, but implemented differently. It also helps keep weight small to avoid overfitting. Adam usually implemented L2 regularization for controlling overfitting, but it did lead to very curious results, which were outlined in the paper Decoupled Weight Decay Regularization that introduced AdamW. Adam with L2 regularization could degrade so bad that stochastic gradient descent with momentum, regularized with L2, outperformed it in some benchmark. The gist of why this happened when L2 regularization is used with adaptive gradient method is that it leads to weight with large historic parameter or gradient amplitude being regularized less than they would when using weight decay. The reason is that the gradient of the L2 term is proportional to the parameter themselves. So this can lead to suboptimal update, especially when the parameters are large, and it will affect both the first moment and the second moment here. The trick to sidestep that is to simply leave the loss alone to not affect the adaptive learning rate and the gradients. Instead, you can decay the weight directly after the parameter update. This is in a nutshell what AdamW is doing. There is some confusion between L2 and weight decay, though, because L2 is rightfully called weight decay sometime. So for instance, whether you apply L2 regularization or weight decay to stochastic gradient descent, you can get roughly the same formula with the two regularization method if you rescale by the learning rate. However, when there is an adaptive gradient method like Adam or AdamGrad, they do not lead to the similar formula. So let's dive into the formula now in details so we get a good sense of what's going on before implementing it. If you watched the other Adam video I've done last week, you can catch it up because I explained the whole Adam thing in details. I'm going to go through it still, but I will focus on the regularization part. So if we start at the regularization, you get this big thing which might be hard to understand what's going on, right? The only thing that is changing here with Adam is literally this little tiny part here. Because remember, weight decay is basically just like the weights minus learning rate times the weight decay parameters times the weight squared, or like just the weight. So this is what's happening here. You have these two things that are multiplied by that. So you actually can put it out. So this is the learning rate times our parameter here, weight decay, and then our previous parameters over there. So these two are hyperparameters, right? These two, and these are just your weight. And this, right, is the rest is the weight update from Adam. So AdamW, right? This is where you have your name. Adam is here. And then the weight decay is over here. If you were to do L2 regularization, you would have changed the gradient over there. And like you can read the paper to go through the full derivation, but because there's some adaptive gradient things going on here, it won't just change one thing and you can recoup the same thing as weight decay as in stochastic gradient descent. It will change the first moment and the second moment, and this mess up the whole thing, especially with very large weight. They don't get regularized as much, and then you get like a degradation. So you can actually see it here, right? So this is Adam with L2, and this is Adam with weight decay, right? This is from the paper, the original paper. And basically in this grid, you have like the amount of regularization here in both cases. And then you have the learning rate here, right? So this is gonna like a grid with like a bunch of hyperparameters. Basically what I mean is that lower mean less error. And the surface with AdamW is better here when compared to Adam with L2. That's all you have to know here. And if we compare it with stochastic gradient descent, we get these two, right? This is on a Cypher 10 dataset. So Adam with L2 kind of suck, right? Like this. Stochastic gradient descent with L2 and weight decay, they are kind of similar in terms of surface. And here AdamW is kind of similar to stochastic gradient descent with weight decay. So that's kind of it. Because like, remember, the issue is that this very simple algorithm was better than the kind of complex Adam when regularized. Perfect. And here we have a kind of another view of it. This is from the PyTorch documentation, right? And then this is where they're doing their weight decay, right? Over there, you have like the learning rate times the weight decay parameters times the actual weight of the model. It's just another way to see it, because that thing, right, get just copy paste here and you get the same thing, yet your minus whatever. So there's many ways to write it, but like overall you're gonna end up with that. So right, if you haven't watched the video on Adam, you can watch it now, but I'm gonna go quickly on like what the other parameters mean, because it's not that complicated, right? If you just go back the tree, right, of like what everything means prior, you see that Adam is actually stochastic gradient descent with momentum, and the arm is prop algorithm, right? The both idea are integrated here. So you have stochastic gradient descent here with the very vanilla type of optimizer. So you have your weight minus learning rate times the gradient, right? And you do that on some batches. If you add the momentum, it's kind of the same thing, but you keep track of like the previous gradient step that you did. And then you have a whatever parameter, alpha, for the momentum, and this will tell you how much of the pass you should keep. So this is kind of you can think about it as a heavy ball rolling, and then it has some weight. So whatever happened in the past now holds some weight. So this is an idea that is included into the first this first box for Adam, right? The elements are a bit changed because it's using an exponential moving average, but it's the same idea, right? So here you have the past step with the first, what we call moment. Here you have your gradient, and here you have this parameter, which is the same as the alpha, but in this case it's called beta 1. If we climb up a bit the linear tree, you have this idea of AdaGrad, and in AdaGrad it's a 2011 idea where what if we had a scaling of the learning rate per parameters. So this is where the adaptive learning rate idea comes from. This adaptive learning rate will change the gradient update per parameter. So it means roughly that like instead of applying the learning rate through all the dimension, right, of this ball rolling, you will apply it more aggressively in some dimension and less than others. So long story short, like when you get the gradient in place, you're gonna divide the learning rate with these adaptive gradient scaling factor, and you have one per parameters in this case, and it's a big diagonal matrix here. So here it says extreme parameter update get dampened, while parameter that get few or small update receive higher learning rate. 1 year later, Armis prop came in, and it's the same idea, except that you have kind of a window moving average that is going on, right? Like an exponential moving average that is going on, and you have this forgetting factor right here that will help you like slide this window a bit, right? So same idea as AdaGrad, and you see it's over here. It's the same structure as this one, and you have like you hear your gradient squared exactly like this here, but it's not a summation. It's really like a moving average that is going on here. Now this idea is what is seen over here, right? It's the same thing that is seen over here, and you have a beta 2, which is this other parameter that you can play with. Usually it's 0.9 over here and 0.99999 here, 39 actually for this one. Now these two, right, there's something gonna happen to them, and then you're gonna have the momentum element here, the first moment, right, that will scale the learning rate, and you're gonna have the second moment element that will also scale the learning rate. So both of them are scaling it in their own way. Now this whole thing, when you start it out with the initialization at 0, it's kind of a bit erratic, right? So there is some duct tape that is applied here with the bias correction for the first element. So you see when we're at the very first element, let's say at 1, we're gonna get, let's say for B1, 0.9, right? So you're gonna get 1 minus 0.9, so a very small number, right? So you're gonna have this divide by a small number, so you're gonna scale it up, right? But as we're, let's say, approaching a larger time step here, let's say B100, you're gonna get like a very small number because you're gonna do 0.9 100 here, right? So you're gonna get effectively 1 minus 0, which is 1. So this will not be applied after some steps, right? So this is just duct tape at the first, just to start this thing out, to get like these things to start to accumulate and all the stuff. So now that we know all this, let's actually implement it in code, and you'll see it's not that complicated. So you have the whole problem statement, and remember, this is an important bit. The Adam optimizer and the AdamW optimizer start when you have gradient. AdamW has nothing to do with accumulating gradient. So this is taken care of by the AutoGrad algorithm and the backpropagation. So you start off with gradient that you have, and you start with a bunch of like arrays and parameters that you can play with, and then you make one update step, right? So this is the whole point of that optimizer. If we get to it, right, what do we have? We have the weights, right? So this is our parameters. We have the gradient that has been given to us by AutoGrad. We have the first moment vector, the second moment vector that you need to keep track of. It's not something that you just like use once and it's done. You're gonna use it and you're gonna return it. Then you have the integer t, which is our time step. And this is important because this is gonna be used to do the bias correction. You have the learning rate, the two hyperparameter beta 1 and beta 2. So beta 1 for the first moment, beta 2 for the second moment. You have the epsilon. This is just so that we don't divide by 0. And then you have the weight decay coefficient here that is used for the learning rate times weight decay times the parameters. And in this case, we just return the new weight, the new m, and the new v. For these two, don't return the bias corrected version, right? Because then it will mess up the whole thing. You just have to return in the next iteration, the new m and the new v. Step 1 is this one, right? And it's to calculate the first moment. First moment calculation. And this one is pretty simple. It's m equal beta 1 times m plus 1 minus beta 1 times g, which is a gradient. Step 2 is to calculate the second moment. So this thing, same structure, but here you're doing gradient squared and you have b2. So here in this case we call it v. You have beta 2 times v plus 1 minus beta 2 times g, right? So step 3 and 4 is to bias correct m and v, right? So this is what we're doing over here. In this case, it looks like this. So you have your m that you just calculated, you have your v that you just calculated, and you do 1 divided by beta 1 and 2 times exponent t. M corrected equal m divided by 1 minus beta 1 exponent t, and v corrected equal v divided by 1 minus beta 2 t. Remember, this is just duct tape at the start. So now, step 5, what do we have? We have the actual update of the parameters. Here you can do it many different ways, right? But I find it useful for your own understanding to just like do literally Adam and then do the weight decay, because then you realize it's literally just one line that you add at the end. So in this case, it looked like this. So you have your previous weight, so W, minus learning rate times the m corrected divided by the square root of v corrected plus epsilon. What do we have? We have W equal W minus the learning rate times the m corrected divided by the v corrected square root here plus our little epsilon, right? That's where we're at. And then finally step 6. This is where we're gonna do our weight decay. And here it's pretty simple. We can just take this whole thing and do the W equal W minus, and then it's like learning rate times lambda times the parameter W. That's it. So W equal W minus learning rate times the weight decay times the parameters. Then we're gonna return on step 7 the tuple for the next iteration. So here in this case it's gonna be W. We're gonna have our new M and our new V, not M corrected or V corrected, M and V. And we should be good to go here. And yes, we got it right. So that's it. So if we recap, right, you have the whole general Adam kind of flow where you have your first moment and second moment calculation. right, with like the exponential moving average. You bias correct to duct tape the initialization as 0. Then you actually do the update of the parameters with the mix of momentum and RMS prop. And finally, you decay the weights after the update step. I hope this was useful. Don't forget to like if it was the case, and see you all in the next one.